So our next speakers have said that they, and I quote, and let me find the quote. Where is the quote? If you let us on stage, we will never finish. We had to cull 2/3 of our content, and it's still over 30 minutes. So what I have done is they've you don't remake them. Okay, maybe she does. They've recorded their talk. They're going to be available in the Discord to have chats. So we are going to play their video. But if you want to ask questions, Kronicd and Swarley will both be in the chat, and they're going to be talking to us about the Bonzi Chip. So I believe there it is. I pressed somebody presses that button and it comes on stage. So we will make that happen.
Today to do my ComfyCon presentation with you.
Yeah, I heard about that.
It's called
some sort of
Bonzi Chip, the Pitfalls of
Buddy
Success
theme talk. But really what we're here to talk about is PCB design and manufacture. So, how you can get things set up for your own projects and be like, I want to make an electronics. And then you could do that. Yeah. All right.
Yeah, exactly. And we're going to use a case study that we actually did, which was creating a mod chip for the Nintendo Switch. So let's talk about that. Okay, so some of you out there probably don't know what Nintendo is, so we're just going to give you a brief explanation. So they're a card company from the late 1890s. Now, they've been going since then and predominantly manufacture trading cards. These days, they manufacture extremely expensive trading card games featuring mutant
that sounds good,
and other sort of weird creatures. But on the side, they also dabble with electronic games. Now, not many people know this, but my uncle actually did work for Nintendo in the 90s, so I had the best cheats and hints for Pokemon and Zelda. I was able to get him used.
Yeah, I mean, the only part of that is that's not true at all. Cool. Your uncle worked at Sega.
Your uncle worked at Sega. Stop lying.
Okay, so mods. What are modifications? So modifications, when we're referring to video game consoles, are generally to enable the execution of unsigned code. So these things can exist in hardware and software. There's always a bit of both, but if we're talking about a soft mod, we generally mean it's impossible just with software. And if we're talking about a hardware mod or a hard mod, we're saying it requires you to solder things in or otherwise attach new stuff to your console to make it happen. In our case, we're going to be talking about a hard mod.
So, in this instance, the target console was the Nintendo Switch, and the modification chip was a device that performs an exploit against the hardware in order to enable arbitrary code execution. So the Switch Tegra X2 system on chip had a vulnerability that when voltage glitched can be abused to execute custom bootloader, which skips the signature check during the boot code loading process. So this vulnerability has been known for a number of years, and there's a lot of modification chips that were on the market that provided the ability to exploit that vulnerability and then load unsigned code in and enable custom firmware to run on the device. A lot of these use custom designed PCBs fitting a targeted, and they had proprietary FPGAs which perform the actual voltage glitching attack and deploy the payload. So these, as far as mod chips go, they were very well designed, very user-friendly. They had a lot of simplification features so that they reduce the amount of soldering and other dangerous operations required by installers. Nice little ribbon cables that neatly fit in where they needed to be soldered on, and some other guardrails to reduce the risk when working with critical components. However, they're extremely expensive. We're talking in the realm of between $150 and over $300 Australian. At one point, I remember seeing one of the HW Fly chips going for about $450 when they were running scarce.
Look at that. we instead sat around and didn't mod our switches. And then this post showed up on GBA Temp, and this person's got a picture here of an RP2040, so a very, very cheap Raspberry Pi Pico,
Raspberry Pi.
based on the RP2040 chip there. So really, really cheap. And yeah, suggesting it's clearly a fake. Am I right or not?
Yeah, so enter the age of the PicoFly. Mod chip based on the Raspberry Pi 2040 Zero, which is a small little micro Pi. And in order to install it, you pretty much only needed some wires, a few resistors, a few MOSFETs, and the copy of the firmware.
So the original PicoFly firmware couldn't actually be used to run backup games. It was able to run homebrew, so you could boot Linux and things like that. And this was an artificial limitation imposed in the firmware. However, later on, someone did decrypt and document how this firmware functioned. And, moving forward, the developer then released it with its full feature set there, and at a later time, open sourced the whole thing. Now, we just figured while this was going on, we'll start building our own PCB to run the firmware on, because we figured, the full feature set is going to inevitably show up, and it did. So good times.
Okay, so now we're going to move on to going through an example board that we've rigged up with just some basic components to give you a sense of how to design and manufacture a PCB. The first and arguably most important step of your design process will be to produce a schematic. So this is a logical layout of the components that will be used within the electronic system and how they are all connected together. So just a few notes on the symbols used within the reference example we have here. We've got capacitors indicated by these two break lines. We've got these ground labels indicated by the sort of upside down pyramid and G and D. That basically means that that pin connects to the ground plane of the system. And we've also added some labels. So you'll note that there's a label with a 5V, a label with a 3V3, and those labels appear multiple times throughout the document, throughout the schematic. Anywhere that that 5V label exists, that will provide a physical connection between those two components that form a network. So, as you can see on the pin header in the bottom left-hand corner, we have pin 2 is connected to 5V. Now, on the USB connector at the top left-hand corner, you'll note that pin 1 is connected to 5V. So they exist in the same physical electrical network. So those things will be connected together, and that just gives you a simplified ability to, I guess, isolate or compartmentalize your design. So you can have, you could have those two components on separate sheets or in separate parts of your schematic, and know that they are physically connected, but you can simplify those components and make them appear more modular. It's important to use reference documents when designing your schematic, especially the manufacturer specifications for each of the components you use. That'll help to make sure that your pinouts, etc., are correctly wired up. As even though you might have identical components, maybe one manufacturer decides to use a different pin layout than another, and you don't want to be assuming anything in this situation, because that'll end up with problems down the track. However, don't be afraid to question design choices made by a particular manufacturer, especially when your use cases vary. So, for example, the Raspberry Pi 2040 reference documents, which were fantastic, helped us to design most of the board. However, there were a few things that we decided we didn't need for our specific use case. One example being the power regulator, which we decided to place on a disposable part of our board, as once the device is being powered, has been installed into the switch, it will be powered by the switch itself, and the power lines going into it will be clean. So we didn't need that additional component, which was also one of the largest components on our board. So we were happy to get rid of that. Oh, and the green X on the schematic basically means that that pin is not connected. So in this instance, you can see on the USB connector on the top left, those two pins 2 and 3 aren't connected. That means that the manufacturer knows that those lines are dead and not to try and wire anything up to them. Okay, now, each item in the schematic needs to have a part associated with it. So that means that you need to go through and hand select each particular component from the inventory available to that manufacturer. This provides the manufacturer with the physical details of each of the components, for example, the size, the footprint, the pin layout, etc. And also gives you the ability to ensure that you have your pinouts and your wiring, etc., correct based on what the manufacturer's specification for that component is. It's important to note that there is no such thing in this space as like a generic resistor component or capacitor. Each thing needs to be hand selected. Okay, and you've got some considerations to make when you are selecting your specific parts. So obviously price is a huge factor. The cheaper the component probably is what you want, assuming you're selecting from multiple iterations that look identical, specifications wise. However, you've got to consider minimum order quantity. A lot of these components are designed to be purchased in large batches, so it might be 100 minimum quantity required before you can purchase a specific component, or 1,000 or 10 or 5 or whatever the specification for that is. And depending on what batch you are looking to produce, it may be cheaper to go with something that's a little bit more expensive but offers you a smaller minimum quantity or no minimum quantity to order.
Now, I'm just going to explain the concept of a basic versus extended part. When these are made, they're put together by a machine called a pick and place, and the pick and place has all these parts that are connected to it in a series of bins and spools and things like that. A basic part is always attached to the machine, and an extended part is something that a human has to go and get and plug in and set up on the machine. So there's there's an extra fee for any extended part because of a human's involvement. So we try to avoid those where we can.
So when you're actually assigning the components that are going to be used on your PCB, we use the JLC PCB website, which links quite nicely with Easy EDA, the schematic designer we used. So our process was basically to search the JLC PCB website for the specific component we needed, find one that suited our requirements, and then grab the product code and run it through Easy EDA, which we'll talk about in a second. It's important to note that when using these websites, they're kind of terrible, just in general. Things like applying filters or any other search criteria will 90% of the time just fail to produce anything meaningful. So you want to kind of keep your search term as broad but encompassing as possible. So for example, here we're using the term 47 because we're looking for a 47 ohm resistor, and 0402, which is the footprint size for that particular component. As you can see, we've also ticked the box for basic parts because we only want results that are basic parts, not extended parts, as we don't want to incur extra fees by having them included. And that's returned 2 actual resistors, and the rest are like capacitors, which is just interesting, but sure.
Now, it's worth also noting that when you do this, you need to go into the information sheet for each of them, because you're going to get, in your results, you're going to get, 4.7, 470, 47K, 4.7K. You're going to get like 47 nanofarads, 47 picofarads. And then search engines are just weird. You're going to get stuff where just 47 was in a part number or something like that. So you really do need to check and make sure that the item that looks right really is exactly what you wanted. Yeah,
absolutely. So important. And So in this situation, we've clicked on this and we've opened up this resistor. Now, as you can see in the listing at the top right there, we've got things like the minimum order quantities, the price for those specific quantity tiers. As you can see as well, the more you buy, the cheaper those items get, and how many are available in stock. This measurement of and dimensions of the resistor rather, and you can also download, for example, the data sheet for that specific product. So again, always important to check everything and make sure that it does actually meet the needs of what you're going to use it for. But once you've done that, then you can go back to your easy EDA, find your schematics and hit place component, search for the product number, which will come up with that particular component, and then you can place it on your schematic.
Cool. Now, once you've got your schematic all put together and the parts are all what they should have been, it's all assigned, you can then go and press Convert Schematic to PCB. Now, I just want to mention the general process we're talking through here is pretty much the same no matter what software you're using. In the general flow of things, but the specific placement of buttons and parts libraries, that's where it's going to be specific. So this is generally applicable stuff, which is what I'm trying to say, which is good. But once you hit that Convert Schematic to PCB button, it will give you something like we see on the right, so it'll create a new diagram, and this is your physical schematic. So this is physically where your stuff is going to be. And you can see there we've got the parts, like we've got our voltage regulator here. Then we've got some capacitors, some more capacitors. We've got a USB connector and a pin header. So we've got these things, and you'll see there's these little purple lines between the pins coming off them. That shows what needs to be connected to what. And you can use that and drag things around and position them. So let's have a look at that. So what you can see here is all the components that were placed on have been moved into place in this diagram at the top here. So I've moved them in. I just dragged them around to where they looked good. And, as I'm dragging them, I can see those little blue faint lines moving around to get a good idea of, should I rotate this to the left a little bit to, should I rotate it 90 degrees so it's going to be easier to connect all those things up, for instance. Now, down the bottom here, so the absolute cheapest boards have 2 layers. Now what that means is you can do your design on the top and the bottom. If you're willing to pay more money, you can start having like layers that are in the middle of the board too, and you can run your connections through those as well. But we're doing a simple 2-layer thing. So the way I normally start with this is I'd add a copper ground plane. So I'd just say on the bottom side, just make it a solid piece of copper for the moment, and connect that to the ground network, which is specified in the top right here that I'm pointing to. And that way, it'll tell the software this part should be copper, it should be connected to ground. But don't worry, if we try and draw traces through it or whatever, it'll sort of intelligently remove things to the side so it doesn't bridge it all together. It's cool like that. But we're going to have a simple one here where we do all our copper traces on the top and all our ground connections on the bottom. Then comes routing, and routing is honestly really annoying. It's the process where we use our copper traces to connect everything together. So all the parts that should be connected to ground will be connected to ground and all together, and the parts that are supposed to be 5 volt will all be connected to each other in the 5 volt network, and so on. Now, pretty much any software you use, it's going to have a button that says auto route, where it's going to use various algorithms to try and produce a result that connects everything together as it's supposed to be. In my experience, that generally ends up fairly terribly. So on the left-hand side here, you can see we've got one where everything's connected. That's using auto routing. And, well, look, it says broken there. It's not really broken. It would probably work. But, I don't like it. I don't feel it's as efficiently done as it could be. So on the right, I've gone through and manually drawn all the traces. So just like in this schematic, where we manually just click to connect things together. We do that exact same thing in the PCB layout, and then you can like drag the bits of copper around to get angles prettier and things like that.
Okay, so then once you've routed all your copper traces and everything, it's all looking pretty, you can generate a 3D mock-up of your PCB, and that gives you kind of the view of the entire thing, including things like components that might have sizes, or as you can see, the headers sticking out there. So that'll, give you a good idea as to how it's going to look when it's produced. And from this, you might be able to identify, actually, you know what, that header port being there is potentially a concern, because that's supposed to be a low profile part of the board. Maybe we'll move it around or remove it or whatever. So
you can also at this point take a bunch of screenshots of it and post it to people online and act like you did something, which is always enjoyable.
That's a very important part of the process. Okay, then we manufacture. So once you've got your designs and everything, you can basically send them off to a factory for them to produce. Although it's fairly simple, obviously things can go wrong. For example, maybe the parts you've ordered, specifically some of the less or more obscure parts, might no longer be in stock, and you might have to look for alternatives. And if those have different footprints or whatever, perhaps you might even have to adjust your PCB layout and designs. So this process can be a little bit tedious and have a bit of back and forth with the factory. In our experience, we were very lucky with the manufacturer we use. They identified a couple of issues with our board that they were more than happy to work with us to solve. One being the the layout for a footprint for the LED that we chose, because it was a custom contributed schematic. It didn't actually match the product dimensions perfectly, so when they went to put it on the board, it didn't fit. So they helped us to devise an alternative where we were able to actually fit it correctly. And that worked, and 4 out of 5 of the boards that we got, one just came without an LED.
Yeah, so whilst like the changes we were able to make were actually pretty small, so we got something where it's like a part of the pad on the PCB overlapped with like a part of the connectors on the LED. So it's really flimsily attached, but 4 out of 5.
Yeah, not bad.
Yeah.
And Peter eyeballed the size of the USB connector and said, "Yep, that'll be fine." And I'm pretty sure I said multiple times, like, "You've checked that? Are you sure?" And he's like, "Yeah, no, it's fine." And sure enough, the pins weren't quite wide enough, so you do have to kind of jiggle it in a bit of an angle in order to get it to connect correctly.
Now, it wouldn't connect at all on any of my USB ports. Like, I think you use like a Surface Pro or something. The USB ports in that worked, I think, if you did it on a weird angle.
Shimmed it with some cardboard on an angle, and it worked fine.
Yeah, so there you go. It's all right.
Okay, so this is the board we produced, the Bonzi 2040. As you can see, we did an initial batch of 5. These were our kind of development test boards, which also are production boards, incidentally. Mm-hmm. And we wanted our board to be quite a small profile. Now, if you look at it, it does actually look quite large with all the USB nonsense on there, and there's a huge power regulator, etc. However, as you'll notice, the board is perforated around the middle. So the intention is, once you've programmed the board, added the firmware to the Raspberry Pi, and confirmed everything's booting correctly, you can literally snap the board along that perforation line, and then that reduces the footprint of the device when it's actually installed in the switch, which we thought was a very neat feature. Right, so installation and testing. Yeah, installation of these devices is not for the faint of heart. I will absolutely disclaimer this presentation and say, if you want to attempt this yourself, do so at your own risk. You run a very real risk of bricking your unit or perhaps causing irreparable damage. Mm-hmm. So you might not like. It sounds obvious, but these components are extremely small, like really, really small. And it's not until you're kind of trying to solder between two capacitors or resistors or whatever on the board that it becomes very apparent how small these components are.
And also to be clear, like you might see all the like installation diagrams and go, oh no, that looks fine. Every diagram you look at is taken with a microscope. I just want to make that clear.
Yeah. Yep. So the pads aren't really designed for hand soldering. The pads on the actual console as well. Usually these are interacted with machines, which have a higher degree of precision and can get temperatures exactly where they need to be, etc. We're working with, a cheap soldering iron and some cheap solder and some cheap flux and some overlarge wire.
Basically, everything we used was bought from AliExpress.
Correct. It is very much recommended to get a digital microscope. It will help you actually see what you're doing a bit better. With all those caveats out of the way, this is a very doable project, and electronics are surprisingly resilient. Both Peter and myself caused some problems with our console during the process of this, and our console still worked after we intervened and were able to identify what the issues were and fix them. So as long as you've got a steady hand, a steady supply of beer, and some Taco Bell, you can probably get this done. So this was my installation of on my Nintendo Switch. You can see I've got my digital microscope connected to my laptop in the top left corner. I've got my pine sil soldering iron with the ultra fine tips. And we were using, I think it was 0.1 millimeter wiring for these joints, which is extremely fine, but still actually feels quite large when you're working with such small solder points, so that's important to note. I managed to get my console working, it booted, it was absolutely fine, and then after some usage I found it no longer booted at all. Once I took it apart, I realized that the DAT0 cable had dislodged, so the device no longer booted, and during the attempt to repair that, I accidentally removed my DAT0 port, which is more or less the only point that can be used for that particular trace. There aren't any other points connected from the one that I used, other than directly under the CPU, which is...
I was going to say, there is another one, it's just under the CPU.
It's completely inaccessible. So I managed to repair that by resoldering a trace with whatever was left of the pad. And at that stage, I kind of got cold feet. I bought a $30 mod chip from AliExpress and installed that in my console.
See, that's the thing worth noting. Like, on our way through this process, we manufactured, everyone else was doing it too. So by the time our mod chips arrived, AliExpress was flooded with better products.
Knockoffs. Yeah, exactly. And for example, the HW Fly released their Pico Fly chip, which again has all those nice little features that you expect from the $150 ones, but for $30.
Yeah.
And principally in this case, things like ribbon cables, and the chip actually mounts in the eMMC port rather than using hand soldered connectors across the unit. So
it's like the hardest parts to solder, you just don't have to with the more
you just don't have to worry
stuff.
about it.
So if you're wondering, it's like, oh, can I get one of these chips you've made? No, just get the better one from AliExpress. That's not the point.
Exactly. Yes. Yeah. 100%.
So this is the problem I had. So you can see on the upper left there, my mod chip is in place in my Nintendo Switch, sitting on top of the heat shield. It's all soldered in there, and you can see this nice bit of wire going into the Switch. Now, what you don't see here is the original one, where I had maybe half a meter of wire just coiled up in there, and that caused some problems.
Apparently it didn't like that.
So I removed a bunch of that and ended up with like what you see in this picture, which is still too much wire, but it's better. And the other thing I realized, at some point it was all working. I was playing games. I was enjoying it. I'm like, why is Wi-Fi not there? So I took my console back apart, started looking around, and noticed. So you can see under the microscope here, there's a shot. So this is a capacitor that's really mangled. It's in bad shape. And here was one that was completely obliterated and removed. And just below it, you'll see my new capacitor that I ordered from AliExpress. I think I got 20 of these for $1. And I then moved that into place and soldered it in. But just to illustrate how tiny that is, you can see here, this is my index finger for scale. And you can see there's the part that needed to be soldered into place. And, under the microscope, it looks pretty reasonable. On the finger for scale, it does not look reasonable at all. So, if you're wondering how, I moved it into place with like a toothpick and then soldered it on using the iron very, very carefully. That worked fairly well. But, it's a pain.
Yep. So, some just general advice, like if you're looking to do this kind of stuff, if you're going to mod things, have a look at common values for capacitors and resistors when you're doing your purchase order for example, wiring and solder and flux and all the other stuff you'll need. Just add in a couple of either strips or books of capacitors and resistors at the size that you need, and potentially the common values. That way, if you do, for example, like Peter, take out a couple of caps during the process of installing, you've just got them on hand and you can basically repair it and continue on quickly. Otherwise, you've got to wait for it to be delivered from AliExpress, most likely. Yeah, so one thing we talked about doing with the next variant of our board is on that top part where, we've got the perforation line above there where the USB port is, we talked about adding in some extra resistors and capacitors of the common values. Again, if we look at the price for a resistor from that previous slide, it was about a fraction of a cent. So, you could add to 5 to 10 of each without actually blinking, as long as you've already got them in your board on your design or whatever. The additional cost is going to be absolutely negligible. But then, if you need to, you can remove them, and you've got them there.
Absolutely. So yeah, just having those spares on hand coming with the thing is fairly good. Yeah. And it's also worth saying, when I looked into it, where the value of like, a set of capacitors or resistors or whatever was less than a cent, it got rounded to zero. So I don't think we actually paid for many of the capacitors we used, which was really cool.
All right. So this is the intro slide.
Yep. This is where we introduce ourselves. I had this theory that it's like you probably care more about who we are after you know what we've talked about. Yeah. So I'm Peter, also known as ChronicD. I'm a person who does things sometimes.
I'm Clinton, also known as Swarley, and I also do some things. And we made a mod chip. So thanks for attending our ComfyCon presentation. I really hope you enjoyed it.